So this is the continue to solve the problem 3, practical kinematics 2, and in the first portion of the video of the solution, we solve the relative velocity of KB to KCs. So now we want to find out what is the acceleration of KB relative to KC. So we do the same, start with acceleration equation. So we have acceleration of B equal to AC plus AB relative to C. And with this one, we can draw the diagram. So as you can see, B is on the circular track. It's a curved track, so it's curvilinear motion. And keep in mind the acceleration, we have two components: tangential components, which is tangent to the path, and then normal components of acceleration direct to the center in there. So you have acceleration in tangential components, which is here 2 meters per second, and the normal components will be go to the center. So that is the normal component. So let's show it in here in the diagram for AB. So curvilinear. The first one is ABT, tangential components. ABT, tangential components. And that problem is 2 meters per second square. You can see there. So let's move. Meters per second square. And the other components is the normal components, which is go to the center. So these two components have to be a right angle, and that is ABN. And what is ABN? It will be velocity of that car B over rho at that instant, over rho, not rho square. So we can velocity of B in that sentence equal to B 15 meters per second square. The rho here is 100 meters, so you can plug in here equal to 15 square over 100 meters square. You have that equal to 2.25 meter per second square. So there are two components for curvilinear motion. Two components for acceleration: tangential, tangent to the path. If it deceleration, so it will be opposite to the motion, like these scenarios. And the normal components, as already mentioned. And AC, they already solved there. It also deceleration. So it's 3 meters per second going up, opposite to the motion going down. 3 meters per second go up. 3 meters per second square acceleration. AC go up. And then we plus the unknowns. AB relative to C, so we have X and Y components again. We have A, B relative to C, X, A, B relative to C, Y components. And let's assume X, Y positive axis as usual. And now the tricky part is we need to know what is the angles of these two. So when we use scalar, we can projection. So as you can see, the normal components of these angles what is the angles in there. So we have zoom out here, and we have two angle there. So as you can see there, if we consider this is a right triangle, this is 30 degrees, so that one have to be 60 degree. 60 degree. And when it right angles, the normal and tangential normal, so that angle have to be 30 degrees. So from that, we can have the angle here 30 degree, and because right angle, that is 60 degree. So with that, we can have all the direction and magnitude of each component except the x and y components of the relative acceleration of B relative to C. Then we just break it down into x and y components. Let's do it x. Positive axis x. Then we have will be a negative 2 sine 30 degree. And then positive 2.25, and in that case also sine 60 degree. AC 3 meters per second square going up, so it will be 0. And then we have A, B relative to C in x direction. And from that we have A, B relative to C in x direction equal to 0.9 49, and the unit is meter per second square, and that is a positive number, so it will be go to the right. So that is the x components. Similarly, we have y components of the relative acceleration of KB relative to KC. So we project that again. So positive 2 cosine 30, also positive 2.25 cosine 60 degree equal to 3 meters per second square for AC going up, so it will be positive 3, and we have plus A, B relative to C in y components. Again, one equation, one unknown, so we have AB relative to C in y components equal to negative 0.1429 meter per second square. Negative means opposite to our assumed direction. In the diagram, we assume AB relative to C in y direction going up, so this have to be going down. 0.1429 meter per second square going down. So from that we can have the x components, y components. So go ahead to find out the magnitude of the this acceleration. B relative to C magnitude equal to square root of the xy component 0.949 square plus 0.1429 square, and that number it will be 0.0959 meter per second square. So that is the magnitude. How about the direction? So let's draw that down again. We have x 9.49 go 0.949 go to the right, so you have this is x component 0.949 meter per second square go right, and y components go down smaller 0.1429 meter per second square. Again, the resultant it will be the diagonal of this rectangle, so we have that will be A, B relative to C, and the angles we want to find out is here, that theta. And of course, as you are already familiar, theta equal to inverse tangent of opposite. Opposite in this case is 0.429. Adjacent 0.949. So angle theta equal to 8.757. 57 degree, and your answer it will be acceleration of car B relative to C equal to 0.959 meter per second square at 8.57 degree clockwise from positive x-axis. Okay, so you can write down in there AB relative to C equal to 0.959 meter per second square at 8.57 degree, and this case clockwise from positive x-axis, and that should be the answer. By now, you should be mastering how to solve both relative acceleration equation or relative velocity equation.